You will. Grandfather was also an organic chemist, so he also didn't like the math.
I'm definitely here to get back into the organic side, but yeah.
I said you'll like
I
it.
forget exactly which
Yeah.
school, but around the state of the layer, you know,
Your cup of
there's
tea.
several. Oh, no, I remember now, it's Rogers.
Oh, did you say this talk won't be her?
Rogers.
It's a bit.
He went to the
She's
one.
she's here, so
She's had a bit of. I mean,
She's
like.
getting pizza.
I know,
None of my children have that.
I always liked math.
It's really interesting,
The first grade that they had the
learn
music.
about new stuff. So
Yeah.
Okay, I think we'll get started. So thank you for coming. It is my immense pleasure to introduce Dr. Hasini Perera, a professor in chemistry at the University of Colombo, Sri Lanka, which is the alma mater for her, Dr. Vijay Tunga, and myself. So it's really wonderful to have someone here, right? She is also one of my best friends since college days. In fact, I knew her since our middle school because we went to the same high school, middle school as well. So we've been knowing each other for a while. We used to be sitting next to each other in seminars, just like you are right now, and being lab partners, studying together during college years, just like you are. So it's really my immense pleasure to introduce her, and she obtained her PhD in analytical chemistry from Oregon State University, and her research focus is on electrochemical sensors, analytical instrumentation, corrosion science, and chemical education, with publications leading international journals and several granted patents. She has received multiple awards for research excellence and academic outreach, and right now she's a Fulbright visiting scholar at the University of Minnesota, Twin Cities in the US. So please welcome Dr. Perera, and let's actually we'll welcome her, but at the same time, Arden has something to do as well.
I feel blessed to be here. I think it's wonderful and be very welcoming. And so thank you, Irosha, for that wonderful introduction. And so before moving on with today's talk, I think I'll just give you a little bit of an introduction to where I come from. I'm sure you have heard it from Dr. Namaratna and Dr. Vijayaratna. But let me just tell you a little bit about our country. So you see the location. It's located it's an Asian country located in the Indian Ocean, right next to India. So it's also known as the Pearl of the Indian Ocean. You will see why it's called the Pearl of the Indian Ocean, because one thing, it's an island nation. So being an island nation, it's around the country, you have very nice beaches, sandy beaches, blue waters, warm waters. You can swim in the sea anytime you want. And you have nice sea life to see. We have sea turtles and very nice, if you want to go snorkeling, you would have a wonderful time in there. Like in National Geography, what you see, you can see it really in Sri Lanka. And not just the sea, we have like wonderful variety of animals everywhere. You can go safari and see herds and herds of elephants, deers, monkeys are all over the place. You don't have to go in safari, you can just go anywhere, you will see monkeys. A lot of birds, tropical birds, migratory birds. So it's a wonderful country. If you ever get a chance to visit, I'd like to invite you to the country. And so it's about that. And it actually has a very rich culture as well. So what you see here is called Tigiriya. It's a UNESCO heritage site that's built in 5th century. And it's a fortress that built on top of a rock. It's the people, the engineers are amazed today even how they did all that on top of that rock. Right, so the pictures are from the rock fortress. They are famous and they're said related to the famous Ajanta pictures in India. And you have other cultural heritage. It's the main religion in the country is Buddhism. So you have many stupas that were built. So this temple, the third largest brick, it's the largest brick building in the world and one of the third largest ancient buildings. And so that's a bit about the country. And other than that, there are so many other interesting places. If you are, if you have looked at travel documentaries, I'm sure you must have heard of a famous Nine Arches Bridge. And you have wonderful, like we have a hill country in the middle of the island where you have wonderful waterfalls and tea plantations and so on. And so that's a little bit about the country for you to get an idea where I come from. And so let me just really quickly tell you about where we had the education, just like Dr. Hirosha told, from the University of Colombo. It's the oldest university in the country, and we celebrated 100 years in 2021 with COVID, but we did celebrate the 100 years in 2021. So we'll be celebrating 105 this year. And so it's that's where my undergraduate degree of chemistry honors came from. And my PhD is from the United States itself, another wonderful university, University of Oregon State University. That's the place where I actually started my research on electroanalytical sensors. Okay, so that's, I think, about it. I'm going to tell you for the introduction. So then we will move on to my talk today, which is electroanalytical methods, principles, and real-world application. So it's mostly for the students. So before we move on to electroanalytical sensors, I think something that is important in electroanalytical sensors, you really need electrodes. So there are 3 different types of electrodes in there. Right? So you should know all these 3 types of electrodes. So I'm hoping you would interact with me and try to give me some answers. So then I know that you kind of get what I'm talking about, right? So these, if you take a look at the electrodes, you have 3 different types of electrodes. The first one is, we call it the working electrode, or it's also termed as the indicator electrode. Right? So the working electrode is the one that is interacting with the analyte of your interest. Right? If you are interested in knowing the concentration of a certain analyte, let's say H+ concentration. Right? So working electrode is the one that is interacting with that, and so you would have that one. And then in electroanalytical sensors, the 2 parameters that are usually monitored are the potential and the current. Right? So you have your working electrode, and if you want to measure the current, you would have to have another electrode. And that's because for the current to flow through, there has to be a complete circuit. Right? So you have your working electrode, and then you have to have another thing. So for example, if you think about lighting up an LED bulb, right? Being the city of Christmas lights, I'm sure you all know about the how to do an LED light. So you have a dry cell and you have the LED, and if you have a copper wire, if you connect your dry cell to the LED, just one side, will the bulb light up? It won't, right? So it has to be complete, right? You have to take another copper wire, connect the other end of the LED to the dry cell to complete the cell. So the exact same thing in electroanalytical sensors as well. If you want to measure the current of your working electrode, you have to have another setup so that it completes your circuit. Right? So your counter electrode or auxiliary electrode, so these are the terms that are used for this electrode, is the one that is completing your circuit. Your current flowing through the working electrode has to go through the counter electrode, then you can measure the current. Right? And the other term that you're going to measure, which is the potential. So you cannot measure a potential of just one point. You would always be measuring the potential of a potential difference. So you want to know the potential of your working electrode, you would have to have another point where the potential is not going to change, and you measure the difference in potential. So once you know the difference in potential and you know the potential of the constant value, then you can go and find out the potential of your indicator electrode. Right? So if you measure the potential, you would know, or you would need a reference electrode. Right? So the reference electrode will have a constant potential, and you use that to measure the potential of your working electrode. Right? So are you guys familiar with reference electrodes? No. Okay. So there are there are a lot of reference electrodes, but there are three very common reference electrodes. The main one is called the standard hydrogen electrode. That's the main one, but that's not being used very much today. Can you think of a reason as to why the standard hydrogen electrode is not used today? So the standard hydrogen electrode is having a redox reaction with H plus, takes up one electron, and it forms hydrogen, H. And then two hydrogens together forms the hydrogen gas. So this equilibrium has to be maintained in the standard hydrogen electrode. Anything that you can think of? Why are we not using the standard hydrogen electrodes? What do you know about hydrogen?
It's flammable. Is it flammable?
Exactly, yeah. So it's not, I mean, it's not easy to handle, like it's a gas, right? So mainly you have to maintain a certain potential, a certain pressure. So it's not easy, it's not there. And the other reference electrode, other two, one is silver chloride reference electrode, right? So that's the most commonly used reference electrode. And then you have another one, it might come to you if you're doing your reading, which is the calomel electrode. Calomel electrode also, the redox potential, the redox reaction is you have Hg2Cl2, takes up two electrons, and it forms Hg. What's Hg? It's mercury, right? So the mercury, you know, it's not very safe to handle, so people are not very much interested in using the calomel electrode as well. So the most common reference electrode that's being used in mostly is the silver chloride electrode. Right? So if you take a look at the silver chloride electrode, so you have to maintain this redox reaction for it to maintain a constant potential, right? So the reduction reaction that is taking place, you have silver chloride, right? Silver chloride is a solid, but what is silver chloride made up of? What are the ions? Silver chloride, it's a solid, but any solid is having something called a solubility product, right? It's going to dissolve into the ions that's making up that solid. So what do you guys think? What are the ions that are there in silver chloride?
There's 3 people on
What ions?
Silver and chlorine.
Exactly. You have silver and chloride. So you have Ag plus and Cl minus, right? So when you have a Ag plus ion, your electron is provided. So Ag plus can take up that electron and reduce into silver solid, right? So that's basically what you see, silver chloride. It has Ag plus and Cl minus. So this electron is taken up by Ag plus in silver chloride and it reduces into silver solid. And chloride ion remains as a spectator. Okay, so I'm just trying to explain here how the potential is maintained constant. Okay, so Dr. Hirosha told me that you all know the Nernst equation, right? So this is the Nernst equation that I have used for the silver chloride half cell here. So you write that the E is for the potential is equal to E naught. That's the standard reduction potential, which is a constant value, right? And then you have RT divided by NF, right? All constant, gas constant, temperature. N is the number of electrons that is there in the half cell reaction. F is the Faraday's constant. And La and the activity, if you're not very familiar with the term, it's closer to concentration, right? So we can just talk about concentration. So you have the concentration of silver solid, concentration of chloride ions, and concentration of silver chloride, right? So the concentrations of the solids are going to remain constant. So you can substitute these with a 1. So, and all that gets incorporated into the standard there, and you can see the potential of this reference electrode is only dependent on the chloride ion concentration in there. Okay? So this is basically how we maintain the whole potential constant. Now you can see the potential is dependent on the chloride ion concentration. So if you maintain the chloride ion concentration constant, then the potential of that electrode will remain constant, right? So, so you have this setup, and you can see your silver wire. It's coated with silver chloride, which is the solid, and it's immersed in a KCl solution of 3.5 molar. So 3.5 molar means the KCl is saturated. So if the chloride concentration changes, because it's saturated, you can always provide chloride ions. So it will maintain a constant potential. Okay? So that's basically how the reference electrode is having a constant potential there. And have another question for you to think about. Now I told you we are going to measure in electroanalytical techniques potential and the current, right? I told you to measure the potential we need the reference electrode, and for the current you need to have an electrode and your circuit has to be complete. Why can I not use the reference electrode to complete the circuit? Why do I have to go and put another electrode in there? Make things complicated with 3 electrodes, and why not use this same thing to measure the current? What's current? What comes to your mind? When you say current, current is what? Movement of what? What's flowing through the system? It's the electrons, right? So it's the electrons or charges flowing through the system is what we call as current. Okay? So can you see in the reference electrode, right? This equilibrium will be disturbed if currents start flowing through the system. If this equilibrium is not maintained, you will not have a constant potential. Okay? So you cannot have a current flowing through your reference electrode, because then the potential of that, the constant potential will not be there. Okay? So that's basically why we need all 3 types of electrodes. So remember, in any electroanalytical techniques, you need either at least 2 electrodes or 3. Right? You have the working electrode, counter electrode, and the reference electrode. Okay. Right. So that's the types of electrodes, and then we will move on to one of the techniques, which is potentiometry. Right? In potentiometry, we are. Can you take a look at the term and tell me what are we measuring? Current or potential? It's potentiometry, right? So you're measuring the potential. It's very easy, right? The name tells you what it is. You're measuring the potential, and that potential is correlated to the concentration of ions in the solution, right? And we measure the potential when no current is flowing through the system. Can you guys tell me now, like, what are the electrodes that we have to use in potentiometry? We talked about 3 electrodes. You're measuring potential. So what are the electrodes? Anything?
Reference.
Exactly. We need the reference electrode because you're measuring a potential difference. So you have to have a constant potential. You need the reference electrode. And what's the other one? What's the other one? Every system has to have this electrode. That's the working electrode. I mean, you have to, there has to be something that is going to interact with the analyte in there, right? So in potentiometry, you have two electrodes. One is your working electrode, and the other one is your reference electrode, right? You measure the potential difference between the two and, extract information based on that, right? So in this case, I'm using an ion selective electrode. Your working electrode can be anything. It can be a metal, right? You can use a zinc wire to measure the concentration of zinc 2+ ions in the system. You can use a copper wire to measure the copper 2+ ion concentration in the system. Or you can use something that is inert, something like platinum, and measure the concentration of any ion in the system, right? So it doesn't have to be an ion selective electrode, but ion selective electrodes are the most researched topic in potentiometry, right? So that's why we're going to look at the ion selective electrodes. Have you guys, any one of you have used any ion selective electrodes? No? Have you ever used a pH meter? Yeah, so that's an ion selective electrode, right? So that's something that you have used. I'm sure all of you, even if you haven't used, at least you have heard of it, right? If you go to a doctor and get a lab report, most of the time pH is there in there, right? So that's an ion selective electrode. Okay, so what are ion selective electrodes? They are converting the activity or concentration of a specific ion into the potential. So like I told you, it's the simple principle. So there are several types of ion selective electrodes. The first one is the most common, where we use glass membrane. Right? So sodium silicate lattice, the glass membrane, as the ion selective component in there. That's the one that we talked about, the pH electrode, the most common. And then you have solid state membrane electrodes. So you have the membrane, which is a solid lattice. Right? So like, for example, the fluoride ion selective electrode, you have lanthanum fluoride lattice as the ion sensing membrane, and that's another type, right? And then you have these compound electrodes, like all the first two electrodes, you're using them in the solution, right? You place it in the solution and then measure the concentration of the species, and it's related to potential. But in compound electrodes, you can use them to measure gases, right? So, for example, you will have a pH electrode that is covered with a membrane that is selective to carbon dioxide, right? So, using that, you can use the carbon dioxide concentration using compound electrodes. And the one that is mostly used in research is the solvent polymeric membrane electrodes. We call them liquid electrodes. Right? So these are the ones, if you get interested or like you decide to go for any sensor development, these will be the membranes that you will be mostly working with. Right? So let me tell you a little bit about these solvent polymeric membrane ion selective electrodes. So these the membranes have a component that is selective to the analyte of your interest. So that's the one that we refer to as carrier or the ionophore. Right? So ionophore, you can see, now I've just done a little diagram there. Ionophore has like a half circular shape in there. You have so many ions in the solution. The one that this ionophore is going to be selective to the one that is machine, like a lock and key mechanism, right? So how? So these are the ones that are going to be selective towards the ionophore. So it's the exact same concept, right? You have a ligand that is selective to a certain ion. So that ligand is the one that we refer to as the ionophore. And then for an ion to come in, right? So if you take a look at this membrane, you can see the membrane is electrically neutral. you have a positive and negative here, positive and negative. So it's a neutral membrane that we have. And your ligand is not having any charge. So what happens if you want to take this positively charged blue circle into the membrane? Is the membrane going to remain neutral, or is it going to be, the neutrality, is it going to change, or will it remain neutral? You have 0 charge in the membrane. You're trying to get one positive in. If that one positive comes in, what happens? It's no longer going to be 0. It's going to be a charged membrane. So that is not something that nature likes. Nature likes neutrality, right? So the potassium, or like the positive charge to come in, then something that is positive has to leave the membrane and go out into the solution, right? So these membranes work only if you have these ion exchanges in the membrane. So the positive ion that is selective to your ionophore will come in, but when it's coming in, something that is not as selective will go out of the membrane, right? So these are the two working components of the membrane, the ionophore and the ion exchanger, and they are in like a matrix of PVC and NPOE. So it gives you more like a plastic kind of membrane, that like a rubber, like I'm sure you all know the balloons, right? So you have the rubber nature. So that kind of a nature is there in these PVC membranes, right? So these are the type of ion selective electrodes that mostly being researched. So how do they work? So you have the sample. Let's see now, the example that I'm taking is a potassium ion selective electrode. So the membrane that we talked about, L is the ionophore that we talked about, the selective ligand, and R minus is the ion exchanger, the negative, the counter ion of the ion exchanger. And so in the membrane, we have a constant concentration of potassium, because before we use this electrode, inside you have an inner filling solution that has a high concentration of potassium chloride, and overnight we condition in potassium chloride as well. So now, because the membrane is selective for potassium, there is a high concentration of potassium in the membrane. Okay? So these sensors also work using the Nernst equation, right? So if it's electroanalytical chemistry, one equation that you should know is the Nernst equation. That's the equation that we use over and over again for ion selective electrodes. So also the Nernst equation works. So the potential at the phase boundary, so the phase boundary we are talking about is the membrane and the sample. So potential at this point is related to a constant value, RT divided by NF, Ln, activity of potassium in the phase boundary. So this is the concentration of potassium in your sample, okay? And divided by the activity of, or the concentration of potassium in the membrane phase, okay? So this is something that is remaining constant because it's saturated, it has a constant amount. So the potential that is developed is related to the concentration of ions. And a common way of representing this one is the phase boundary potential is equal to E naught. And we have substituted all these with their respective values. R, 8.314, which is the gas constant, joules per mole per Kelvin. The temperature, we substitute that in Kelvin, like around 298 Kelvin standard temperature. And Faraday's constant, 96,500. And this Ln is converted into log by multiplying by 2.303. So once you do that, we end up getting this value, 0.0596. Okay. So the reason why I told you that is the response of an ion selective electrode is determined using this, right? So if you take a look at this, this is a calibration plot of an ion selective electrode. Any electrode, before you use, you have to calibrate, right? Even the pH, I'm sure when you used it, you calibrated your pH meter, then you used it. And so calibration, you will be using this equation. So you have your y-axis is the potential, and your x-axis is going to be the log concentration of the analyte of our interest. Then what's going to happen to the slope? The C is going to be the charge of the ion of your interest. Let's say if the potassium ion, potassium has a +1 charge, right? So then what's the slope going to be? Slope is going to be 0.059 volts, right? Or like you can see in the picture here, 59 millivolts. So the response, once you develop an electrode, you calibrate it, and based on the slope, you can see whether it's giving the correct response. Okay? So what do you think? If you're using a chloride ion selective electrode, and you're calibrating this chloride ion selective electrode, what kind of a slope do you expect to see?
Negative.
Negative what? The value?
Or negative 0.05.
Exactly, right? So because you're just using the charge, you can actually, based on the slope of your electrode, you can determine what's the charge of the ion that it's responding, right? So you will have a negative 59 millivolt slope. If it's calcium, then what happens? You're dividing it by +2 here. So you have something like close to negative 30 millivolts, right? So likewise, you can see once you develop a sensor, whether it's working properly, whether it's responding properly, based on the slope of your calibration plot. Okay? And the other important parameter of the ion selective electrodes is selectivity. I mean, you don't need to use a sensor and determine the concentration of an ion in a solution. You would want it in a very background of so many other ions, right? You don't want to make a sodium chloride solution and make a sensor to determine the concentration of that sodium chloride, right? You would want to know the sodium chloride concentration, let's say in your blood or your plasma or in some water that you're drinking, right? So you would not have just sodium ion in that solution. You would have so many other ions in there, sodium, potassium, calcium, right? So the ion selective electrode has to be very selective to this ion, right? So if you just take a look at this, this is the exact same equation here, but instead it's taking into account the response of all the other ions that are there in the solution, right? So if you take if this value, this is what we refer to as selectivity coefficient. Selectivity coefficient has to be a very small value for your other ions to not give a response to your electrode. Right? So if you take a look at the pH electrode, if you consider a pH of, let's say, 12, you're using a sodium hydroxide solution of pH 12. What's the concentration of H plus in the medium? The pH is 12, H plus concentration is how much? pH is the minus log activity of H plus concentration. So if your pH is 12, the H plus concentration is going to be 10 to the power minus 12. Sodium ion concentration is 0.01, right? So you have very high concentration of sodium ion. For sodium ion to not give a response, and for H plus, that is in 10 to the power minus 12, to give a response, this value has to be extremely small. So whenever you make an electrode, it will be a really good electrode if you have a very small value for this selectivity coefficient. Okay, so I think we will move on. So ion selective electrodes, there are so many interesting research areas that is happening. I've talked about where you have solutions inside. Instead of but having a solution is not very easy to handle. So now the research is going on to develop all solid state electrodes, where you have solid contacts inside. But when you have solid contacts, it's not as good as the liquid. So people are trying to find new transducer material, and then they try to find a material that has good interfacial stability and drift mechanisms, and you're trying to find new ionophores to detect the ions that are there available. And miniaturization and wearable sensors, what you see in the picture here is like a headband where you have ion selective electrodes printed onto the headband, and you're exercising, but you can get the concentration of the ions, and based on the ion concentration it will tell you whether you have to stop your exercise, whether you have to go and hydrate yourself. So all these things are the new developments that are coming in ion selective electrodes. Okay, so I think that's all the things that I'm going to talk about potentiometry, and very briefly we will talk about another electroanalytical technique, which is voltammetry. Right? So if it's voltammetry, it's a collection of techniques where relation between current and voltage is observed during the electrochemical process. Right? So you're measuring the current. Now in the previous one, we measured only the potential. Now in here, we measure the potential as well as the current. Right? So if we measure potential and the current both, then what are the electrodes that we need? You need all three electrodes. You have you have to have your working electrode, because that's the one that is responding to the analyte of interest. And then you have to have, you're measuring the potential, so you have to have the reference electrode, and you're monitoring the current as well. So you have to have a counter electrode. Right? So in voltammetry, you will be using 3 electrode system. So these 3 electrodes, again, just like I told you in the earlier case, any conducting material can be used as the working electrode. And another commonly used electrode material in voltammetry is mercury. You can use a hanging drop of mercury or a dropping drop of mercury as the working electrode in voltammetry. Those are called polarographic techniques. They have like a special name, polarographic technique, but again, because of the health issues related to mercury, they are not very common today. Okay, but just for your knowledge. And just like, so this is like a voltammogram. What we do usually is we change the potential at the working electrode and we observe the current. Right? So if you have an ion will reduce at a given potential, not every potential. Right? So that's called a standard reduction potential for different ions. Based on this reduction potential, you can actually go and find out the ion that is being reduced. Okay? So like until the standard reduction potential is reached, when you change the potential, there's not going to be any current flowing through the system. But when the reduction potential is reached, you will see it's reducing. So the current is increasing and it will come to a constant value, which we call the limiting current. Right? So in these techniques, we change the potential of the system and measure the current. And that is related to the concentration of the analyte. So based on the increase in concentration, you would have increase in current in the system. Okay, so again, just like the previous system, you can measure the current and plot a graph with the concentration. So you have a calibration plot. Based on the calibration plot, you can determine the concentration. Right? So just like any other technique, I think you've used a spectroscopic technique where you use the calibration plot. The exact same concept is used. Okay? So there are so many voltammetric techniques. I'm not going to go through everything, but this gives you more like a small idea about a few commonly used voltammetric techniques. So linear sweep voltammetry is what you saw. You just increase the potential, let's say from 0 to 1. And when the correct potential is reached, the analyte will reduce. Right? So you would see a graph like the one that you saw in the previous slide. There are other common techniques, which is CV, which is cyclic voltammetry. You cycle the potential, right? You increase the potential from 0 to 1 and goes back from 1 to 0, 0 to 1, 1 to 0. So then you would have more like the similar way. You have no current flowing through the system, and then the correct potential reaches, the current starts increasing. And then you have a constant current, then it starts decreasing. Now at that time, we are change the direction of the potential. So whatever is reduced now will oxidize. So you will have this and then the backward curve coming in. Right? So that's the type of voltammogram that is used in cyclic voltammetry. And then you have differential pulse voltammetry or square wave voltammetry. These are used to increase the sensitivity of the system. And so the sensitivity is increased. So you would have more of a peak rather than a plateau, which is much easier for you to detect and determine the concentration. And another common voltammetric technique is the anodic stripping voltammetry. If you have very minute concentration of the analyte ions, you can first concentrate them, pre-concentrate them, and then apply a potential, and then oxidize them back into the system. So you would have a better signal. Right? So actually, these are the very commonly used voltammetric techniques. So a very brief look into that, because the time I can see is running out. So let's just take a look at some applications in voltammetry as well. It's used in quantitative as well as qualitative analysis. Like I told you, you can determine what is there, but it's not conclusive. You can just say, okay, this could be the ion that is available in the system. And you have so many quantitative applications. You can analyze single components in samples. There are multi-component samples can be analyzed. You have environmental analysis, clinical analysis, pharmaceutical analysis, all using these techniques. Right? If you move on to anything to do with electroanalytical technique, this is a very helpful technique and you will be using it, definitely. Okay. So actually, that brings me to the end of this talk. And so thank you very much. I would actually first like to thank the Fulbright program for sponsoring this visit and making sure that I could come here to there. And definitely to the Lion College community and all of you for being here. And when I talk about the Lion College community, I would really like to thank Dr. Grafton for all the support that's given. And I don't think she's here, but I'd like to thank Rose, who did all the work and made a wonderful itinerary. And, last but not least, definitely Dr. Hirosha Navarata, who's been doing everything from the beginning till the end. Right? And thank you all for being here. And so if you have any questions that you have, I can answer.
What got you interested in this section of chemistry?
Oh, you mean electrochemistry? My interest, which is actually from just the PhD. I just went, I went in, wanting to study photochemistry. This was the project that was available, so I started on that, thinking I'll later move on to photochemistry. Never moved back, so that's how it is.
And you all are welcome to come down and ask your questions too. It's kind of, they have 1 o'clock left.
Nice to meet you and visit with you. How long will you stay? How long will you stay?
I will see you person in advance. We know your mother-in-law, I believe. Lara, Laura. I think